This video is for topic number 19, solving quadratics in standard form using the quadratic formula. As always, when we are solving quadratic equations, we are looking for x values that make the equation equal to 0. As we are finding these solutions, which are the answers, or also known as zeros, roots, or x-intercepts, turning a quadratic into factored form or intercept form via the process of factoring is still our preferred method. We would still like to factor, as it is quicker for us to find our solutions, zeros, roots, x-intercepts if it's real. However, sometimes we encounter quadratics that cannot be factored, but graphically have clear solutions. So another method must be utilized. Take, for example, 2x squared minus 10x plus 6 equals 0. We can start off by making these numbers smaller, dividing out the GCF to get 1x squared minus 5x plus 3. But when I attempt to do my factorization, we find that there are no factor pairs of 3 that add up to negative 5. But looking at the graph, we see that we have two clear solutions, two x-intercepts, two zeros, two roots. How is this possible? Well, it's because this quadratic does not factor nicely, but we still must have a way to go ahead and find our solutions. This method is going to be using the quadratic formula. You've seen this before in Algebra 1. It is x is equal to negative 1 times b plus or minus the square root of b squared minus 4ac, all divided by 2a. This is simply a formula we could use just by substituting the values of a, b, and c and simplifying. We are able to get our answers. So let's go ahead and take a look at how I can come up with these answers, perhaps in exact form, from our quadratic. So we'll start off by dividing out the GCF, making the number smaller as we did before, and we will in fact try to factor each time as we did up above. I won't illustrate that again, but we did it up here. So now, since we realize we can't factor this quadratic, we are in fact going to use the quadratic formula. We're going to identify the constants a, b, and c. A is in front of the x squared, b is in front of the x, and c is the constant term. And we're going to go ahead and use the formula. Now, I like to do underneath the quadratic form, underneath the root first. So I'm going to go ahead and do that calculation. B squared minus 4ac, substituting in the values of b, a, and c, gives us negative 5 squared minus 4 times 1 times 3. Negative 5 squared gives us 25, and then negative 4 times 1 times 3 gives us negative 12, which gives us a value of 13. This is the value that we'll be putting underneath the square root, along with the values of b and a into the appropriate locations. So negative 1 times b, plus or minus the square root of what was underneath the square root here is 13, 2 times 1. Now, I'll go ahead and do the multiplication here and simplify the root if possible. Root 13 off to the side does not actually simplify down any farther, so we are just stuck with the square root of 13, so that will stay there, giving us 5 plus or minus the square root of 13 over 2. We cannot simplify this down any farther, so this would in fact be our answer. If we typed each of these individual cases into the calculator, we would get the decimal approximations that are listed here as the x-intercepts. We're not going to show that, but you can go ahead and double check that for sure. A small side note on simplifying. So off in the margin here, we're going to talk about simplifying in this quadratic formula. I have two examples, 4 plus or minus 2 root 6 over 8 and 4 plus or minus root 6 over 8. We are only able to divide out a common factor of the numbers that are outside of the square root, and only if they all share a value. So looking at 4 plus or minus 2 root 6 over 8, we are only able to try to divide 4, 2, and 8 by the same number. The 6 is underneath the square root and cannot be used. So down here, 4, 1, and 8, looking at these numbers, I cannot divide each of these numbers by anything other than 1. So this would in fact be my final simplified answer. Versus here, I can divide each of these by 2. So that would give me 2, that would make that a 1, and that would make that a 4, meaning that my final answer, in this case, would be 2 plus or minus 1 root 6, all divided by 4. So I could simplify that down as long as all of the values on the outside can be divided by the same number. Again, we cannot divide numbers on the inside and outside of the root. That is not going to happen. Okay, so very quickly, one other piece of discussion that we need to talk about. If I were to rewrite the quadratic formula as two fractions, so if I were to take this 2a and put it underneath the first piece and the second piece, we should recognize that this, negative 1b over 2a, is in fact our formula for h. Formula for h for a quadratic in standard form. Hey, that's great. Well, that makes the question then that this second piece affects the k value, or another way, influences our k value. Specifically, the b squared minus 4ac really affects whether this graph, where this graph is going to have its vertex, whether it's going to be above the x-axis, on the x-axis, or below the x-axis. So we give a special name for this b squared minus 4ac, and it's called the discriminant, b squared minus 4ac. And it is very, very important in that it determines the number and type of solutions, right? Also, it kind of helps us visualize the graph. So there are really 4 cases. Really, it's 3, but we'll talk about there's actually a 4th case here. If b squared minus 4ac is greater than 0, meaning that it is positive in both of these cases, we get 2 different ideas. If it's equal to 0, equals 0, and if it is in fact less than 0, means that if it's negative. Okay, well, let's start off with the positive case. When it's positive, it could be one of 2 things. It could be a positive perfect square. So, for instance, it could be 9 or 16 or 25. Or it could be a positive not perfect square. Perfect square. Now, why is this important? Well, we are still going to get 2 real solutions, meaning that our quadratic is in fact going to cross the x-axis at 2 locations in each of these examples. However, with the perfect square, we're going to get a rational solution, and a non-perfect square means we're going to get an irrational solution. What that really means is rational means we're going to get a nice value, like this is going to be like x is equal to 3, or x is equal to 5/2, some type of nice looking value, versus irrational, meaning that we're going to get something like 0.519 that doesn't repeat, or 1 plus the square root of 5, something that looks kind of a weirder answer. Okay, so it is important to note, like, as we're doing this, what type of answer we're going to get, 2 real rationals versus 2 real irrationals, and that all depends on whether it's a perfect square or not. If it equals 0, if the discriminant equals 0, we're going to get 1 real or double solution, meaning that this graph is going to touch the x-axis 1 time in and only 1 spot. Now, and in terms of an equation, this will look like something like x minus 3 squared. All right, that'll be the only factor. It'll appear twice. That's why we call it a double root. And if it's negative, well, if it's negative, it means that we're going to get no real solutions, meaning my graph is never going to, in fact, cross the x-axis. But we know that since it doesn't cross the x-axis, no real solutions, it actually means that we're going to have 2 imaginary solutions instead. Okay, so we should get some type of answer that has an I involved in it. Okay, this is very, very important as we start our problem. It helps us know what the math is actually going to look like as we're moving through. Actually, it's the first thing we do when we do the quadratic formula is we actually do the math for the discriminant, just so that way we can kind of know, hey, what's my answer going to look like? Am I going to have I's? Is it going to be a nice looking value, or is it going to be something weird? All right, there you are. We'll go ahead and get started on the practice.